So yeah, we're going to talk a little bit about how to think about restaking rewards with a view from history. So one way of viewing AVSs and sort of AVS selection is via matching markets. So matching markets are where you have two groups, one the supply side, one the demand side. I guess when it comes to humans, we probably hate choosing one side or the other for that, but each side has a set of preferences and you try to match them. So for instance, in this graph, you can see two sets of people, A, B, C, D on the left, E, F, G, H on the right. And you can see them being matched based on those preferences, and you can also see how one particular match blocks the other ones. So what is a matching market? So matching markets are in a lot of different places. There's, of course, this famous book about it, but I think the most well-known use case is kidney exchange. So that's matching people who are kidney donors with people who are willing to donate. The main idea is that you have a set of goods that are inhomogeneous, but they share some properties. You have a set of demand, which is buyers with constraints, so people who need kidneys, and you want to match them. Now, you might say, hey, look, there's a ton of stuff in crypto that's auctions. Why are we not just using an auction? Well, the TLDR is auctions are really focused on either maximizing revenue or maximizing welfare. They're not really focused on stability. So, if I remove one bidder from an auction, the revenue the auction might go down by 100x, right? If that one bidder was bidding extremely high and it's a first price auction. Matching markets care about stability. If I add or remove a person, how stable are the matches? And how much do they change under perturbations? And so when you think about restaking and thinking about restaking security, you might care a lot more about stability than you care about revenue. The natural representation to think about matching markets is as bipartite graph, where one side is the supply side, one side is the demand side, and you have sort of edges in between them representing successful matches. Usually this graph is static, and oftentimes there's a central planner who does the matching. But decentralized matching markets, like restaking markets, don't have either of these features. Okay. So we can think of restaking as a decentralized matching market. AVSs or services are trying to buy security, stake, from node operators, and they're trying to figure out what the amount they need is. Okay, so let's talk a little bit about how you would think about representing this kind of system. So, like I said, matching markets, they generally have this thing of supply and demand, and we have a similar thing for restaking. We have first the node operators, who are these blue nodes, who are validating the service and sort of making sure these services are live and achieve whatever properties they claim to have. Each of the validators has some stake. That's this sigma to the right. And there are a set of services. So these are AVSs. These could be rollups. These could be MEV auctions. These could be oracles. The third thing is the maximum profit from corrupting a service. So this is sort of, you can think of this as like, when I do a double spend attack, what's the maximum amount of value I could extract? The next thing is the corruption threshold, which is basically, like you have in BFT algorithms of assuming at most 1/3 Byzantine or longest chain, at most 1/2 malicious. This is that threshold. And finally, one major difference is you can have a single node operator validate multiple services. Okay. So now a natural question is, what does it mean to attack a restaking graph? Well, to attack a service, you need two things to hold. First, you need to be able to be profitable. Second, you need to be feasible. So what does that mean? Profitability means, given the set of services, the maximum profit you can extract is greater than the maximum slashing penalty that the network can impose. So this is sort of like the worst case profit you could have. The next thing is feasibility. Feasibility refers to the idea that every service that's being attacked needs to be attacked by a cartel or a group of node operators that has at least alpha S, this threshold stake, to do the attack. Mathematically, this is what this looks like. You can kind of, this is sort of indirectly in the Eigenlayer white paper in Appendix B, but also in this other paper by Dervisel and Roughgarden in this form. All right. So where is this different from proof of stake? So in proof of stake, you would have service 1 and service 2 be completely independent. So in this diagram, they would be secure because the total profit you get from corrupting, which is 4, is less than the total stake that would be lost. But you can have a restaking attack where you attack both services simultaneously. And in this case, it's actually profitable to attack both simultaneously. And the main reason for that is the shared node operator that is common to both of them. So a natural way of thinking about these kind of attacks is a cascade. And so you can think of a cascade as something that is inspired by lending liquidations or liquidations in perpetuals protocols. So how's the cascade work? So first, step 1, you lose a fraction psi of stake, a percentage of stake. You can imagine this is a node going down, someone being DDoS, etc. Second, you can, once the stake is gone, you could imagine that this opens up an attack. So in this example graph, now service 1 is vulnerable to attack by the middle node. And then finally, once that second attack happens, the third attack takes place. So you can see this kind of cascade of loss of stake, first service attack, second service attack. And this is sort of a sort of cascading failure that can occur. And yeah, the correct way to think about this is akin to DeFi more than classical POS security. Okay, so we need to have some measurements for quantifying this. And one place to start is we consider a set of attack sequences. So what I just showed you pictorially is an attack sequence. You attack one service, it opens up an attack on another service, which opens up an attack on another service. You have this sequentiality. And a valid attack sequence is just one in which it's profitable and feasible for every sub-step. So we can define the cascade loss, R psi, as the maximum stake that can be lost in a cascade attack, given an initial loss of size. So you could think of it this way. 5% of stake goes down, maybe someone DDoSes Binance, Binance's validator stops running. After that, it opens up a bunch of attacks on other services, and R psi measures the total amount of stake lost after losing that 5% of initial stake. Formally, you can write it like this. It's sort of a ratio and a bunch of maxima over all the different terms. So you might think, hey, this is a great way to figure out how much stake I actually need in my service. Because if I know that, hey, I'm willing to tolerate losing 5% stake, then I could say, hey, look, when is R psi less than 5%? And how much stake do I need to make that true? Because this R psi metric is monotone increasing in your stake. So this kind of tells you, hey, this is a way of measuring, how much stake your AVS needs. The unfortunate truth is there's a lot of graphs where R psi is 1. So for very small perturbations, the entire stake kind of gets slashed or burnt. And I'll show you a quick example of the construction from this paper, which should be out soon, which is you can look at this graph as a pictorial representation of a restaking graph. So each black dot is a validator, and each box is a service. So you can see there are 2 services with 6 validators, the blue boxes, and there are 4 services with 3 validators, the L-shaped boxes. And in this construction, for each of the services, they need at least 2/3. Basically, if they have 2/3 of the number of operators, that they have at the beginning, then they're attackable. And you can basically see if you lose even just one node, you get this cascade where the second the L shape falls through, then the entire box, and then the overall graph. And because this is a tiling, you have an infinite number of these. You can tile the plane arbitrarily. Okay. So slightly less bad news. In this paper, they give this condition that says, hey, if you're very over-collateralized, and we won't talk about the exact definition, then you can bound your cascade risk. So that means, hey, maybe you should get enough stake to meet this over-collateralization condition. This is very similar to a DeFi type of result, which says if you want to avoid depegs in a decentralized stablecoin, you need to be sufficiently over-collateralized, and how much you depeg is a function of how over-collateralized you are. But this condition is so strong that you actually need the sum of the total profits in stake. So a very simple example would be, I have two services, one in which I can corrupt and earn 1 ETH, one in which I can corrupt and earn 1,000,000 ETH, but I'll need 1,000,001 ETH to satisfy this over-collateralization definition, which is crazy, because the 1 ETH service is not trying to attract 1,000,001 ETH worth of stake. So you might say, hey, is this a dead end? And the answer is no. The one thing that we're missing is the incentives the node operators have. If you account for the incentives the operators have, you can actually have a much lower amount of stake. So we'll talk about quickly why that is. So we consider an incentivized restaking graph. So that means there's rewards that each service offers. And now validators are allowed to rebalance. They're allowed to change their allocation of stake to services. So if you look here, you see that there's only the middle node operating both services. But here you can see it became fully connected in response to the rewards. So the idea is that the services can use the rewards to try to adjust the graphs. And for the previous attack, what happens is if the rewards are sufficiently high, you can see that you can arrest the cascade because people rebalance to fill the void in order to claim rewards. So this sort of says, hey, if you have rewards, you can actually have much lower cascade lengths. So one question is how do you actually get this type of result? I'll maybe skip a little bit, but basically, the two things you do are you reduce the power of the adversary. So in the previous model, the adversary could do sort of arbitrary attacks. And the second thing is you make the node operators smarter. So the node operators have to be dynamically adjusting their allocations to AVSs in order for this to work. And just for formality's sake, this is sort of the type of result we prove, which is given enough rewards, you can control this cascade length and make it small. And you can approximate how many rewards to get with a simple algorithm. So in words and no symbols, if adversaries face costs, node operators are smarter, and services pay sufficiently high rewards, you won't lose much in cascading attacks. All right. So the final thing is what are sort of the practical implications? One, AVSs can choose local reward budgets based on how much security they really want. If I'm the 1 ETH node in my example, where there's only 1 ETH worth of profit from corrupting, maybe I'm only willing, I'm willing to account for attacks that take up to 100 ETH total. And so this is sort of a security parameter that each AVS can use. Finally, the vaults and LRTs are actually extremely important for network security. That's sort of what this intimates, which is you really do need this rebalancing around attacks for these networks.